Okay, hello. So we start the lesson today. I just want to finalize this repetition, and then there are a lot of exercises, so I want to give you a little bit more time to practice on your own. And I'm just actually contacting the publisher to see if this is real, that they don't have any solution manual for this book or not. Okay, I have asked Thomas to contact them. So there is something that might be good if I review a little bit, and of course there are some problems I want to leave it to yourself here, so that you can use GeoGebra to solve this problem. Okay, but before that, let me ask you, because I see in the exercises they are asking about local extreme points for parabolas. Yes. So do you remember what was the idea, more or less? So do you remember we talked about parabolas in the previous course? So a parabola has this, it's a generic quadratic equation, yes? Quadratic function, ax squared plus bx plus c. So if I choose a, b, and c, of course here I am assuming that a, b, and c are all real numbers, and of course a is not equal to 0. Then the reason that I'm excluding 0, because if a is equal to 0, what happens? This term goes away, and I am facing a linear function, yes, a first degree function. But I want to keep it as a second degree, so this is why I assume that a is not equal to 0. And definitely the graph of this type of functions is not a straight line. The graph of this kind of functions is called a parabola. I am not defining a parabola for you, okay? So defining a parabola might be a little bit harder or beyond the scope of this lesson. Do you understand what I mean? For example, if I draw something like this, it seems a circle, but there is no guarantee that this is a circle. A circle should have a specific property to be a circle. And what that property is that there should be some point, so that when I measure the distance of all these points from that single point, all these distances are exactly the same. If this happens for all the points on the curve, then I am allowed to call it a circle. Okay? But what I have drawn is probably not a circle. It's probably a rough, good approximation to a circle. Yes? So that's the same thing. You also know a parabola. What's the meaning of a parabola? So we draw a parabola something like this, but if I have a slight different deviation, there is no guarantee this is a parabola. But if I draw something like this, you say this is not a parabola. Yes? If I draw something like this here, is this a good representation of a circle? No, probably you understand that. But I just try to make you understand there is a difference between the exact definition of a circle and what I just draw and say that this is a circle. If I want to tell you what a parabola is, the parabola is this. You need to have a line, and then you need to have another point which is not lying on the line, and then you say that all the points on the whiteboard which are equidistant from this one and this one form a parabola. Okay? So for example, this point here, exactly in the middle, is equidistant from here and there, yes? So this is one point of the parabola. This is called the focus. And this is called the directrix. The directrix. If I have to find the word. Trix. Yes. I will double check this word. Okay. So this line. So for making a circle, I need two pieces of information. One piece is the point, which I call it the center. Another piece of information is a number that would be the length of my radius. If I give you the point and if I give you that length, in principle you can draw my circle, the circle that I'm asking you. So the circle is being specified by two pieces of information, its center and the length of the radius. Yes? If I want to specify a parabola, I need to give you again two pieces of information, but two pieces of information are both objects. One of them is a point and one of them is a line. And I tell you a parabola whose focus is this point and its directrix is this line is the loci of all points that have the same distance from the point and the line. So this is why if you want to really define a parabola, it becomes a little bit complicated. But it's not something that you don't understand. I can try to show you here. So I give you this line and I give you this point and I ask you to show me some points on the parabola whose focus is this and whose directrix is this. Do you agree this is one of those points? Because if you measure the distance from this to that and the distance from this to this line, by the way, distance from a point to a point is clear. You attach them and you measure the line segment. But if I give you a line and I give you a point and I give you the ruler and I ask you measure the distance from the point to the line, what do? Because there are infinitely many points here. So this you need to understand, yes?
You choose the point that is closest to the
closest
points.
Yes, and that comes from this vertical line. So you draw a vertical line from the point to your line and take your ruler and measure this line segment. Whatever this number is, you say that the distance from the point to the line is that number. So is that understandable? The distance from a point to another point is completely clear. The distance from a point to a line, according to what Gustav said, is the shortest distance. Is that understandable? And shortest distance comes from this perpendicular line. Okay, so here, this is one of the points of the parabola, because the distance from here to here and the distance from here to here are the same. But for example, I cannot draw it exactly, but for example, let me for example here, I don't know, if I take this point, if I measure this distance and if I measure this vertical distance, if they are the same, this is also another point on the parabola. Yes, so this is one point on the parabola, this is another point on the parabola. So for example, this point, this distance should be equal to this distance. If that's the case, this is another point of parabola. So you see, point by point, if you do this, you get a shape. That shape is called a parabola. So it's complicated to define it. So do you understand what's going on? It's not bad to see that. So this is a parabola. Of course, in our course, we are not working with these parabolas. We only work with parabolas opening upward or downward. So it means that this directrix shouldn't be a vertical line, which is a horizontal line. And if that's a horizontal line, and then if I have here, then it would be something like that. Okay? So why, for example, this point is not on the parabola? Because if I measure this distance, and if I measure this distance, they are not the same. If these two distances are not the same, the point corresponding to these distances is not on the parabola. If they are the same, the point is on the parabola. Yes? You have questions?
Yeah, isn't this from Math 2C?
Yes, so that's exactly that part we skipped.
Yeah, exactly.
Yeah.
But is this in Math 3C too? Or?
No, but I just want to talk a little bit about the information. Now you have a little bit more mature, so probably you can understand. That part was just in Origo book. It was not somewhere else. So it was not on the curriculum that you need to understand that. But the idea is this. The problem is that I can show it on GeoGebra to get a better feeling, but unfortunately this will not be in the frame. Okay. I will do something. I will find it and send you the link on the Google Classroom, and then you can demonstrate it yourself by just playing around with points, and you see immediately what's the meaning of parabola. But do you have a little bit of rough idea? For example, if I give you this point is not on this circle. Why? Because if I measure the distance from the point to the center, it is larger than the radius. And if I take this point is not on the circle. Why? If I measure the distance from this point to the center and compare it to the radius, it is smaller, so it is not on the circle. Only the points lie on that circle whose distance from the center are exactly equal to the radius. Yes? Now this is the case. If I give you a vertical line, a horizontal line, and I call it the directrix, and if I give you a point and I call it focus, if I ask you, is this point, I don't know, just randomly, is this point on the parabola corresponding to this focus and this line? How do you understand this? The answer to this is yes or no. What you should do, yes?
You should look at the distance is equal.
Yeah, so it means that you take your ruler and connect these 2 points on the one hand and measure this distance, and then you draw a vertical line from here to this directrix and measure this distance. If these 2 distances are the same, then this point lies on your parabola. Okay? If not, it does not lie on your parabola. So in principle, that's an operational way of defining a parabola. You can understand the parabola point by point. Yes? So it becomes something similar to this. So this is why. So for example, what do you think will happen if I make this point close to this line? Do you think the parabola would be wider or thinner?
Wider.
It seems to be wider.
Yeah.
Yes? Do you agree? Yeah. Because, for example, first of all, this middle point is one point on your parabola. Yes? If I want to make it narrow, it would be something like this, yes? Then there is no hope that this distance and this distance be the same. Yes? But if I want to make it wider, is it the case or not? Yes, because you see, for example, here, as far as the distance is higher, this distance also gets higher. So by making this closer to this line, I will make my parabola wider, and by moving it outward, I will make the parabola sharper. Yes? Is that understandable? So these are the things that it's good to know about the parabola. But don't worry about these things. This is not your lesson. But at least, even though it's not your lesson, I don't believe that's very hard. If someone asks you, what is a parabola, at least you can describe. So if someone asks you, what is a circle, you should say that I need to give you a point as the center, I need to give you a number as the radius. Then I can draw your circle. If someone asks you, what do you need for making a parabola clear, specified, you should say, I need 2 things. One is a point and one is a line, so that line and that point does not lie on each other. Yes? In that case, I can construct my parabola by looking at all points whose distances from that point is equal to their distances to the line. All these points makes a shape for me, which is called the parabola, with the point as the focus and the line as the directrix. Yes? Is that understandable? So that's why when I want to draw a parabola, I draw something similar to this, because if you just play around, there are very good demonstrations on GeoGebra. You can play around with these points and lines. You see how the shape of the parabola will be affected. Okay, but if you want to do that, you immediately see that the shape of the parabola is something like this or something like that. You know, there is no, for example, going up and down and things like that. So this is something that you need to discover by doing some mathematics. Here, we are always working with vertical parabolas. Vertical parabolas, I mean the parabolas that either open upwards or open downwards. Yes? And then we want to, we studied them a little bit before. So, except for the shape, if I want to have the properties, so I will have 2 types of parabolas. Either they open downwards So then you see that I have a turning point, okay, or a local maximum. Okay, why this is called local maximum? Because, for example, if you have a coordinate system and you have drawn this parabola in your coordinate system, so this parabola will continue forever from this side, so but it will not go higher than this point. Okay, so the curve is going up, and when it reaches to this point, it turns back. So that is one name, turning point. Okay, and then another one, local maximum point. In this case, you can just call it maximum. Why? And that why this name is also good. The name turning point is good because you go up to here and turn back. So that's a good name for this point. Another name is called maximum. It means that this is the highest point that the curve will achieve. Yes, so both of them are actually meaningful here. Yes, is that understandable? And the reason this local is not that important for you right now, but it becomes extremely important when we go to other lessons. Why we call it a local extreme point? Because this is, of course, a very simple graph. You will face more complicated graphs. You might have such a graph like this. You see, it might happen like this. Yes? So this one and this one are turning points, and this one is, of course, a turning point. But this one is higher than this one. Yes? So if I ask you what is the maximum you should point to this point, what if this point is also a local maximum? Why? Because locally it is higher. If you look at the points in the vicinity, very, very close to that point, this point is higher than the points in its neighborhood. So it is not maximum, of course, because it is not higher than that, but it is locally maximum. It means that it is higher than the points in the vicinity of that point. Yes?
But that is not a parabola anymore.
It's not a parabola. Okay. So this is why the first thing that we studied a little bit in Math 1C was a straight line. A straight line doesn't have any turning points, yes? Doesn't have any local maximum point or minimum point. And then now we increase the degree. A straight line, the degree of a straight line is 1. But now if I increase the degree 1 more, I have to go from degree 1 to degree 2. And then the degree 2 is this kind of shapes that we call them parabola. Okay? Of course, there is a question, why the shape produced by this function satisfies the property of a parabola? This is not a solved question, you know. Why this is a parabola, answering this is not that easy. I'm not telling that this is too advanced, but it needs a lot of effort to understand why, if you draw the graph of this, it really generates a parabola which has this property that I described you a little bit earlier. Yes? But anyway, you need to trust me on that. If you draw the graph of this function, independent of your choice of A, B, and C, it always produces you a parabola. It might be a wide parabola or a narrow parabola or upward or downward. Yes? Is that understandable? Yes or no?
Yes.
Okay. So now, an important question is that, so we might have also another type of parabolas in your lesson. These are the only ones that you will face. Either they open downward and then you have a turning point which is of maximum type, or you might have this scenario. So let me just put an arrow here, meaning that they will continue forever. So yeah, they will continue forever from this side. Oh, this is also a turning point, you see, but here you go down, 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 and suddenly the graph turns around and then you go up. That's a good name again, turning point. But if I want to name it another way, I should call it minimum, yes? Because this is the lowest height of the curve of my graph. Yes? And of course here again, I can say local, maximum, minimum. And I really don't need to emphasize here on the word local because this is the only type of these points that you are facing. Yes? So here, it doesn't matter if you say a local minimum or a local maximum or a maximum. And then there is another terminology. Sometimes when we want to talk about turning points, it doesn't matter if it is a maximum point or if it is a minimum point. The thing that we will discover, we will tell would be correct for both of them. So this is why we use the word extreme point. Okay? So extreme means either max or mean. So if I ask you, for example, of course, if I give you a graph and ask you find all extreme points, what do I mean? I mean find all minimum points and find all maximum points. This is the way that I use the word extreme points. But of course, I can also use the word extreme here as I see in the book. But extreme point here is either a max or a mean, because for a parabola, both of them cannot occur simultaneously. But for more complicated functions, for example, like this, we have local maximum points here, we have local minimum points here. Okay, and when I ask you find local extreme points, I mean find all max and all means. Yes?
If that line were to continue,
yes,
would the minimums still be minimums? Like,
no,
you say
yes, the minimums are still locally minimum.
Okay.
That's important.
But they're not minimum, they're local.
No, because when we say the minimum, it means the lowest possible value. I'm not talking about the minimum, I'm talking about local minimums.
In the area, it's the lowest.
Yeah, in the vicinity, in the neighborhood of that point, it should be lower than the points in its vicinity.
Okay.
In its neighborhood. Yes? Okay. So this year, the big effort would be to find local extreme points for functions. And then this is, so we did it last year without the notion of what we will learn in the future, the notion of derivative. Okay? And this is why we were so limited. Do you remember we discovered a lot of ways to find the minimum and maximum of parabolas? I don't know, if you go back and see the video, I will repeat some of them today. If you see the video, we actually, I think, spent one session and a half just to exercise to find the local extreme points, turning points of parabolas and things like that. But that would be a matter of seconds for you when you learn the notion of derivative. Okay? But let me just remind you, because that's a repetition in the book and I want to follow the book, so let me just repeat how we can find these extreme points. Do you remember at all something or not at all? So let me start with an example. So, for example, let me start with this example: y equals to, let me say, x squared. This is probably the simplest possible example.
Babak?
Yes?
What is the title of this lesson?
It's still the recap.
Okay.
Yeah, we can say this recap number 2. Yes? And that would be the last recap that we will have. Yes? And we will start the new lesson. Of course, the new lesson is also a little bit of repetition. You want to multiply polynomials and things like that. But I will make the questions a little bit harder because now you are more advanced, so you can solve harder problems. And I really emphasize on them because understanding how to simplify things is really, really important. Okay? Okay, so first of all, if you have already trusted me, you need to know, you understand that this is a parabola. Yes? So, because if I ask you what A is, you would say A is 1, the coefficient here. And what B is, you would say B is 2 and C is 3. Yes? Do you remember, because there are two possibilities for a parabola. Either you have a parabola with maximum or you have a parabola with minimum. Which one is that? We have a rule of thumb, of course, if you can use your memory. If you have forgotten, I will actually find it here for you, no matters. But which one of them? Yes?
Maximum is if A is negative.
Negative. But here A is positive, so definitely it is not of this type of parabolas, yes? It is of this type of parabola. Let us see. But can you tell me, if I ask you find the turning point, you realize that this turning point is the minimum point. So how can I find the coordinates of that minimum point? Do you remember something? Or can you rediscover it today now? So what is your point? Your point is to make the value of y as low as possible. Let me just think a little bit in this way. You might think that I have to give negative values for x because my goal is to make y as low as possible. If I start increasing the values of x, do I really decrease y or I increase y? It's clear, if I make x bigger and bigger, I am adding to this y. Do you agree? If I make x larger, y becomes large. So you might say that, okay, forget about positive numbers, because if I start with positive numbers and I increase them, I will increase y. But do you think if I make x negative and negative, do I still make y smaller and smaller? So you see, if I start from a point and make x bigger and bigger towards the positive numbers, this is definitely true. I am increasing x squared, I am increasing 2x, so I am increasing the whole combination. That is for sure. So I need to give up. I shouldn't go to the right extreme, choosing larger and larger x's. So you might think the opposite should be true. So let us go to the left as much as we can. Is this a good idea? Yes?
Not entirely.
Why?
Because x squared will be positive.
Yeah.
So the more
X
you
squared will be positive.
Yeah.
Even if I choose x to be negative, x squared is still positive. Of course, this middle term would be negative. But which one increase faster?
X squared.
X squared will increase faster, yes? So for example, if I choose minus 5, so let me change the color. If I choose minus 5 for x, so let me write x squared, x, 2x. And then here, if I choose minus 5 for x, this becomes 25, this becomes minus 10. If I choose minus 6, it becomes positive 36, and this becomes minus 12. So you see, if I choose minus 7, what happens here? It becomes 49, it becomes minus 14. So you see, when I start decreasing the values of x towards larger and larger negative numbers, this x squared is actually growing faster than the decrease of 2x. Yes? 2x was minus 10, and then the next step it becomes just minus 12, just 2 units decrease. And then it becomes minus 14. But on the other hand, you see that this was 25 first, and then suddenly becomes 36, and then suddenly becomes 49. So it's going faster. So it is clear that I have to optimize how much I have to go to left. Yes? You see, this is a very important. If you go to right, if you go to right values for x, the positive values of x, you are increasing y. Now I realize that if I go extremely to the left, I am still increasing y, not decreasing it. Do you understand? Because x squared is increasing much faster than this is decreasing. So it means that I need to adjust something to optimize something. Yes? So it is clear that when I make x small, yes, the y value becomes smaller. But if I pass some threshold, then the y value again starts increasing. Yes? So this is why I have a minimum. So this is intuition, how you intuitively think about that. Is that clear? So now we want to find exactly that optimal point. So how should we do that?
I think that last when what you taught us is that we change so that we can put it in. You say so you can put in a parentheses and squared. Or
okay, try not to use your memory. Yes, you're right. Somehow that was related to this, but try to see that you can discover it again.
Okay.
So that was the method, was the complete square method.
Yeah.
Yes, exactly. So let me clean this. So what Rocco is saying is that let us use the complete squared method. Yes, why complete squared method is good? If I ask you, by the way, let me test your understanding. If I ask you what is the minimum possible value for x squared, what is the answer? Yes?
0.
0. Is that understandable?
Yes.
X squared cannot be lower than 0. Can it achieve 0? Yes, when I put x equal to 0. So 0 is attainable for this, and this is the lowest possible value. Okay? If I ask you what is the minimum value for this expression, What is the minimum value of this expression? No. No, be careful. Yes? 0 again. But when it is achieved, in this case,
X equals negative.
negative 1. So again, the minimum is 0. But it is achieved when x is equal to minus 1. Is that understandable? Yes or no?
Yes.
So what about this one? What is the minimum? Again 0, and it is achieved when x is equal to 3. Can you tell me why the minimum is 0? Yes, Alan?
If you square a negative number to become a positive one.
Yes. So it means that even if this number is negative, its square is positive. So the lowest possible thing that I can achieve is to make it 0. I cannot make it smaller than 0. Making it smaller than 0, it means that I should be able to find an x so that when I replace x with that value, the whole expression becomes negative, but this is impossible because I'm squaring it. Is that understandable? So this is why the minimum is this. Okay, what is the minimum of this and when it is achieved? Yes?
It's 1
It's 1, and when it is achieved?
when x is 3.
X3. Is that right? Because you already told me the minimum of this part is 0. So this expression is actually assuming some values. Its minimum is 0. Now I am adding 1 unit to all those values. So what happens? All those values will be shifted 1 unit upward. Yes? So the previous minimum was 0. After having this shift, the new minimum is 1. Is that understandable? Okay? So the good idea is to have a complete square. Because if I have a complete square, I really don't need to bother. Immediately, the minimum of the complete square is 0. Yes? And if I have another extra number, the minimum would be 0 plus that number. What would be the minimum of this guy? Yes?
Minus 5.
The minimum is minus 5. It is achieved again at x equal to 0. So we'll learn what to do. When I give you a parabola, you need to make something similar to this. Let me ask you a little bit harder question. Do you think what happens if I have this? What is the minimum of this guy?
0
It's still 0. Agree? When it is achieved,
when x is
it's minus 3. So what is the minimum of this one?
5.
It's 5. It's still achieved when x is equal to minus 3. Yes? But let me ask you another question. What do you think I can talk about this function minus x squared? Can I talk about maximum or minimum of this function? Let me ask you about the maximum and answer me. No, let me ask you about the minimum as before. Answer, what is the minimum of this function? To pick your curiosity, let me ask you, what is the maximum of this function? I was talking always about minimum. Why is that? Isn't it a question why Babak is always asking about minimum of this function and he never asked me anything about the maximum of that function? Yes, Benjamin?
Because there is a maximum.
Can you elaborate a little bit more?
Well, you can construct the infinite.
Speak louder, please.
You can with the system that we have for numbers, you can construct an infinitely large number. So no matter what number you put as x, you can get a larger number.
Exactly. That's a very good statement. So you say that no matter what value of x I put here, if I increase that value of x, x squared will also increases. So there is no upper bound for how the values of this function can get. So this is why Babak is not asking about the maximum of this function because
There isn't any.
there isn't. The maximum does not exist. Okay? Now, the same is true here. Can Babak ask about the minimum of this function here?
No.
No, because if I increase x, x squared increases, but when I multiply it by a negative sign, it decreases. So if I make x bigger and bigger, I am making this more and more negative. So there is no lower bound. So that's not a very sensible question to ask what is the minimum. If I am crazy enough to ask, you should say there is no minimum. Yes? But is there any maximum for this? You have questions?
I was just going to say that there is a minimum if we have a set amount of numbers.
No, because the minimum, so you might say negative infinity is the minimum, but
Sure.
negative infinity is not a number. Negative infinity, positive infinity and negative infinities are not numbers, are symbols for expressing the behavior of a function. Because, for example, if you say 1 million in principle I can start, for example, assume that one step of mine is 1 unit of length. In principle, I can have 1 million of steps and I reach to the point 1 million.
Yeah.
But when I say infinity, practically it's not possible to take infinitely many steps because it will never end. So if you stay here and say this is infinity, I can still go one step further.
Yeah.
Is this infinity? I can go a step further. So infinity, positive infinity and negative infinities are not real numbers. By the way, these are the symbols. You see, it's like a rotated 8. This is infinity. So if I want to emphasize, we say positive infinity and negative infinity. But if someone writes this belongs to the set of R, this is false.
Set of real numbers.
Yes.
Yeah.
The set of real numbers, we say that it contains all possible numbers, but if you say infinity belongs to the set of real numbers, that's a false statement.
Why?
Because that's a number, that's not a number.
Okay, well,
Yeah. So by the way, working with infinities is very strange. Okay, if you have time, we can talk a little bit about that. It was not that easy for mathematicians to talk about infinities. It was not easy at all because very strange and counterintuitive things can happen when it comes to infinities. Okay, so for example, the set of natural numbers, how many elements are there?
infinite.
Infinitely many. And the set of integers, how many elements are there? How many is actually in quotation, yes?
Infinite.
Infinitely many. But which one is greater?
Neither.
Do you think the infinity of the z, the set of integers is larger than the infinity that we associate with the set of natural numbers, because intuitively we say that, okay, z contains everything in n plus extra a lot of negative numbers as well. So which one is bigger?
Neither.
This was actually a very, very important question for the beginning of the 19th century mathematics. And George Cantor actually was the first one who actually tried to understand them systematically. And the answer, strange enough, is that they are equal here in size.
Yeah.
So this is counterintuitive, yes? But it's not very hard to understand that. Okay? So for example, let me try. So you can immediately understand that. So not for this z and n, it's a little bit harder, but let me make it in this way. For example, let me make it in this way. So let us consider the set of natural numbers. Yes? And let me just consider the even numbers. How many in quotation, how many natural numbers do we have?
Infinitely many.
Infinitely many, yes? And how many even natural numbers do we have?
Infinitely many.
Infinitely many. Which one is bigger?
Neither.
Neither. They are again equal in size.
What?
Equal in size. Okay. Okay. The reason, yes, do you want to comment?
I have a good metaphor. It's hard to understand for some people with that. It's like if you have one basket with apple halves and one basket with full apples, and both baskets are infinite, they have the same amount of apples in them, even though one is only with halves.
That's a good analogy.
I understand that because both baskets are infinite. It doesn't matter if the unit is half apple or a whole apple because they're both infinite.
Okay, let me try to convince you in a different way. Okay. There are two ways of counting things. Okay, in principle. So for example, if I give you two bags, in one bag I have some number of marbles, in another bag I have some number of marbles, and I ask you, are the number of marbles in these two bags the same? What is the first thing that you do? Yes?
You calculate them.
Not calculate,
Well, you count how many.
count them. So you just count the number of elements, yes, marbles in one bag, and count the number of marbles in the other bag, and if they are the same numbers, you say that, okay, they are the same numbers, otherwise. But, if you just want to know if, because when you count them, you get more information. If they are the same, they are the same. But if one of them has 5 marbles, the other one has 6 marbles, you can say that the number of marbles in this one is smaller than that one. But let us consider that we do like this. I put my hand in the one bag and another hand in the other bag. I pull 2 marbles out. I don't count them. I correspond them together and put them here. Okay? And then I just do the same process again. I take it 2 and put them here. Okay, what happens? If when this is finished, this is also finished, nothing there, what is your conclusion?
They're equal.
They are equal. So if I can make a one-to-one correspondence between the elements of this bag, the marbles of this bag and the marbles of this bag, even if I don't know the number of marbles there, I can see that they are of the same size. Another example. So in the aula, I put numbers on these chairs, okay? And then I have a lot of students outside. I don't know, but I know the number of chairs in the aula. I say that, okay, go and sit down in the aula. And then I don't need to count. If I just look around and see that every chair is occupied exactly with one person, yes, what I can conclude? I can conclude the number of students is exactly equal to the number of chairs in this room. Even if I don't know how many chairs are in this room, and even if I don't know how many students are there, I can make sure of I may be sure of something. The numbers are the same. Okay? Is that understandable? Yes or no? Yes or no? Okay.
Yeah.
Now understand, let us just draw this analogy a little bit further. Okay, what I do, I give numbers to the chairs in this aula, but of course this is not possible. It should be infinitely big aula to contain infinitely many chairs. But now assume that there are infinitely many chairs here, and then unfortunately suddenly I face infinitely many students outside, and then I want to organize them. So I already know that the numbers and the chairs are this, so I associate a number, an even number to each student. I say that, okay, this number 2 is yours, this number 4 is yours, this number 6 is yours, this number 8 is yours, and then please, because we are infinitely many people here, to make sure that there is not a big mess, this is the rule. Divide the number that I gave you by 2 and find the chair and sit on it. Okay? Then what happens? The person who has received number 2, divide 2 by 1, and what would be the number of that chair if he follows the rule? This person will go and sit on this chair. Okay? Is that any possibility for this person to be confused? No, if he or she follows the rule, yes? And the second person will divide its number by 2. It gets 2 and then find chair number 2 and sits here. Yes? And the same is true for this one and that one. Okay? Let me ask you, is there any person of this number? No, because the persons are already distributed with even numbers. But what would be the chair for this person?
500.
Chair number 500. So, is chair number 500 occupied?
No.
Yes, why not? If we follow, the person number 1000 will definitely go and sit on chair number 500. Is chair 500 occupied?
Yes.
Yes. With how many people if they follow the rule?
1.
With exactly one person. Okay, is it possible that a chair is left empty?
No.
Which chair is empty? If you say chair number 1 million, it is not empty because the person with number 2 million is sitting on chair number 1 million. So is there any chair empty? No. Is there any chair occupied by more than one person if they follow the rule?
No.
No. So what happens? The number of chairs and the number of people should be the same.
Yeah.
So you see, that's the idea. So this George Cantor was actually thinking it in this way, because if I have finitely many chairs and finitely many students, I can count, and I can count the students and the chairs and predict what will happen. They are equal in size. But assume that I don't know how to count. Assume that I'm a small kid, I don't know how to count, but I think kids also know if there are the same number of elements, it's number of students and chairs, the numbers are the same. The good point is that Cantor realized that the idea of counting is meaningless for infinitely large sets, but the idea of making them one-to-one corresponding together is still working. So let us say that, okay, so now I hope that you see more or less in this way the number of elements in the upper set and the number of elements in the lower set are the same. So when it comes to infinities, you need to be very, very careful. Okay. So you started this talk that infinity. So now we have different infinities, and those infinities actually George Cantor not only defined the infinities, he was able also to organize them. We have infinities that are bigger than the other infinities, by the way. That's also very strange. So if I ask you how many real numbers are there, you again answer infinitely many. But that infinity is much larger than infinity of the set of real natural numbers. And then if I ask you how many numbers are between 0 and 1, by the way, I can just organize. So let me ask you one question. That's also interesting. So how many points are there in this line segment?
Infinitely many.
So, yes, in this line segment, how many points do you think you can count? Yes? Infinitely many. Yes? How many points you can count here? How many points? Yes? Which one is bigger?
The second, kind of.
Which one is bigger?
The second one.
They are the same. So how?
So dumb.
No, but how? Because again, the idea of chair and students, yes? So what we do, let me connect this point and that point. So I take my ruler. So let me just do this graph for you. Okay. Okay, what I do, I say that, do you see this point?
Yes.
I corresponded to this point. This is 1, this is 1. Okay? I tell you, there is one point here. I give you the room for that. Just take this one with your ruler, connect it to here, and then go here. So this person will go and find this chair and sit there. Okay? So let us go to the previous chair. The previous chair is occupied by someone there, yes? Because why? I go backwards. So this person is associated to this person, to this chair. So do you think one of these points will be left empty?
No.
So is there any point which is occupied with more than one of these points?
No.
Yeah, well, it's empty because it's
No.
bigger than the other lamp.
No. I'm just telling you the rule. For example, assume that this is a person here. No, so let us call these persons these chairs. Okay? There is a chair here. Which chair is that? I don't know. The number is infinite, yes? But I tell you that if you want to find the person who is sitting on this chair, take your ruler, connect this point to this point. This will intersect this line at one single point. That point is the person which is supposed to sit on this chair, no one else. I don't know, this is not understand, it's not hard. Yes?
Well, it is kind of hard to
No.
add them.
No, if you want to rely on your intuition, it is hard to admit. But if you want to follow the logic, it's a matter of seconds. Yes? Because if you say the number of points here is larger, what does it mean? It means that you can find a point here so that there are not enough points from here to associate it with it. It's not possible. Any point that you choose for me here, it's possible. I just connect this to that. This gives me 1 point. So this point and this point, I cross them over. Okay? This point and this point, I cross them over. Which point do you think there is no correspondence between them? Can you just mention them for me? Any point you choose here, there is exactly 1 point corresponding to this from here. And any point you choose here, there would be exactly 1 point corresponding to it here. Is that understandable?
Yeah.
Yes? Yes?
If you say infinity is always equals to another infinity.
No, I'm not saying. I
No.
just told you that the infinity in R is larger, but this is harder to
But
understand.
tell me, if those infinities are the same,
Yes.
how is it that there are bigger infinities than others?
Okay, but this is harder to tell
Yeah.
because this is the by the way, the number of elements in a set is a fancy name. It's called the cardinality of the set.
Cardinality.
So yes, and the cardinalities, if we have infinite cardinalities, this is a little bit of math 5, a little bit, but cardinality of math we have different infinities. So by the way, so when it comes to infinities, we have a lot of counterintuitive things. So the point is that infinities, some of them intuitively we think that one of them should be bigger than the other one. They are not, but some of them are really bigger than the other ones. For example, the set of real numbers has infinitely many elements. The set of natural numbers has infinitely many elements.
Yeah.
But the cardinality of R is greater than the cardinality of N.
But doesn't it just mean that one has more frequent numbers than the other?
No, frequency is probably, I don't know
Like,
what the word is, but
In the first here,
I mean,
1, 2, 3, 4. In the second
so
one,
we
you
are
have
actually
2, 4,
deviating
6,
from
8.
the main lesson a lot. But
Yeah.
but
It's
yeah,
fine.
that's interesting. But how, I don't know how to. For example, again, you see, if I ask you how many numbers are between 0 and 1, how many real numbers are between 0 and 1?
Infinite.
Infinitely many.
Yes.
And how many real numbers are there? Infinitely many. These two infinities are equal in size.
Okay.
So this is still not understandable, yes, because that's just one portion of the infinity, and that's the whole infinity. So they are of the same size. So the number of numbers here is much, much larger than the number of natural numbers.
But they're both infinite.
Yes, they are infinite, but infinite is one infinity could. I can talk a little bit about that later, okay? But I don't want to go actually deep in. But I just want to tell you that when it works with infinities, you need to be very careful, okay? And this symbol infinity actually, because there are two infinities. One is called uncountable infinity. This one is uncountable.
Sure.
But we have a countable infinity. N is countable. So when you say countable, it means that you can arrange them in a sequence. Okay? So I have 1, and then I go to 2. But for example, one way of understanding this. But can I arrange numbers in real set? No. For example, if I z, what is the next number after 0?
Infinite limit.
So that's the point.
Yeah.
When I go to the set of natural numbers, this is infinity, but countable infinity. So I can say what is the next natural number after 2. You can immediately say 3. I cannot ask the same question for the set of real numbers. That is the reason, one way of understanding why the infinity in R is larger than the infinity of Z. Yes?
Are you saying that uncountable infinities are larger than
Yes.
countable infinities?
Yes. That's
Okay.
that's for sure. Yes?
So, if I understood it correctly, the reason that the real infinity is larger than the natural infinity is because you have one less restriction, so to speak, because you can have an infinite amount of zeros after the point.
Yeah, exactly. Something like that.
So the more infinities that are stacked into the large, like the thing that we call an infinity, the larger it is. It's hard to speak.
Yeah, so if I want to make it very simple, in R, in N, you can start counting. Okay?
1,
The first,
2, 3.
the second, the third, the fourth, it will never end. But you are still counting. I can ask you, if you order these, can you pick up the 5th one? Yes, you can. Even though there are infinitely many, you go and pick the 5th one. Yes? But if I tell you, can you give me the 5th real number, this is not possible. Yes? Because between two real numbers, how many more real numbers are there? Again, infinitely many. That's exactly the reason that the infinity in R is larger. By the way, let me just give you another counterintuitive example. I was so excited when I was at your age and I studied that. So this is very interesting, by the way. I just remembered that. So assume that this is the idea. Assume that you have a bag of marbles numbered with 1, 2, 3, 4, etc., etc. The set of natural numbers. Okay, and let me make it more horrible or something. So assume that here we have 11:59, and this is midnight. You know, many strange things can happen in midnight in horror movies. Yes.
Yeah.
So here you start doing this. This is the idea. You put all these marbles in your bag, and what you do when it is this. So let me make it like this. I put 0. What is the difference between these two times is 1 minute, yes?
Yes.
Okay? So what I do, when time is here, what I do is that, let me just, not to spoil it, let me remember what I have to say. Okay, no, sorry, I have a bag, but I have these marbles all outside the bag. Okay, I want to put these marbles inside the bag. So when the time is here, what I do, I take from number 1 and 10, okay, and I put it in the bag, and I throw 10 away there. Is that understandable? So from 1 to 10, I take it, put it in the bag, take 10 away, and throw it there. Okay, so what is left from 1 to 9? Okay, now I wait so that I am in the middle. The time is going, I am in the middle. What I do, I will take from 11 to 20, I put it in the bag, I throw number 20 out. Okay? And then when time is here, what happens? I take from what? Tell me, 21 to 30, put it in the bag and throw number 30 away. Okay? Of course, what is happening, I have to do this much faster, okay? Forget about these things. But the clock doesn't care about how effort I am putting in this. I am just disintegrating myself. But the time will reaches here. When the time reaches here, I'm asking you, how many marbles are in the bag?
Because you can't.
Infinitely many. It's natural, yes?
Yeah, because you can't reach one if you have to time constantly.
Yeah, okay, but no, I can do that if I am working with real numbers. That is the meaning of another thing. So I can divide. That's the point. This is the main difference between real numbers, the set of real numbers, and the set of natural numbers. In the set of real numbers, I can divide this division continued forever. Okay? So let me understand why there are infinitely many marbles in the bag. Yes?
Well, every like.
Let me ask you this question. Which numbers are not in the bag? Then everyone understands that there should be infinitely many. Which numbers are not in the bag? 10, 20, 30. But every other marble is in the bag.
Yeah.
Except multiples of 10. If you have infinitely many numbers from 1 up to infinity, if you just take multiples of 10 out, how many are left? Infinitely many. Be careful about the exciting point now. So there are infinitely many there. So in each step, I put 10, I throw 1 out. But let me change my idea, okay? Now, I take from 1 to 10, put it in the bag, throw 1 away. I'm throwing 1 away. And then the next step, I put from 11 to 20 there, I take 2 and throw it away. Be careful. Each time, exactly as before, I put 10 and throw 1 away. Yes? Now, the next time, when it reaches here, I will take from 20 to 30. When I put it there, I look for 3 and throw 3 away. Is that understandable? So, our intuition tells me that how many marbles should be in this bag when I reach to this time?
Infinitely many.
Infinitely many. Is that okay? But the answer is
No.
0.
Yeah.
Wait, what?
Yeah, the answer is 0.
Yeah.
So, by the way, this is very counterintuitive. I was really excited when I see the logic. The logic is crystal clear. But the brain wants to resist. Because each time I am putting 10 marbles in the bag, I'm throwing 1 marble out. In one scenario, I will end with infinitely many marbles in the bag. In the other scenario, I will face with 0 marbles in the bag. And now I can cook up the logic for you.
Really confusing.
So, for example, when this is here, when I reach here, which number is not in the bag? In the second scenario, when I reach to the middle point, which number is not in the bag?
1.
1 is not in the back, from 2 to 9 is there.
Yeah.
Yes? Okay, when I reach here, which one is not in the back?
12.
2 is not in the back. When I reach to this one, which one is not in the back?
3.
3. When I go to the next level, which one is not in the back?
4.
So any number is thrown out at some point when I make this smaller and smaller. Yes? This process is complete. The reason behind this is that I can subdivide, okay, this line infinitely many times. Yes? So if we admit this property of real numbers, we have to admit some strange things like this can happen. Yes?
So the reason that the first example was infinitely is because you had a restriction on which marbles you could take out, whereas in this one you don't have a restriction on that.
Yeah. So, yes, because no, the main reason behind this is that because of the properties of the real numbers, we can divide each line segment to half infinitely many times. If we cannot do that, this process will of course stop. So this is very important. When you comes to infinity, there are a lot of counterintuitive things that can happen and you have to be very careful about them. Yes? So this was very exciting when I learned before, because the brain still wants to resist, you know. What is possible? How is it possible? Every time I put 10, I throw 1 away. Depending on the order and the number of the marble that I'm throwing away, I will end up with different results. Huge different results, yes? So when you are working with infinities, be careful. That's the take-home lesson, okay? So anyway, infinity is not a number, yes? Because for numbers, these things cannot happen, yes? That's acting very normal. Okay, so
Where were we?
actually I don't know. So let's go back. So y was, okay, so that was not solved yet. Y was x squared plus 2x plus 3. Okay, so I was talking about this minus x squared.
And then we got a bit off track.
Yes.
Yes.
Okay. So I ask you why we cannot talk about the minimum of this. You motivated me. Why not? So, and then I ask you, what is the maximum then? Can you tell me? So we learned that there is no minimum. Let me compare. Here, x squared, we had minimum. We didn't have maximum. Here, we understood we do not have minimum. But I'm asking you, do we have maximum here? Yes?
0.
The maximum is 0. Understandable. And when it is achieved?
1 to 0.
Yes. So the mix, yeah. And now let me ask you this question. Do you think I can ask about the minimum of this or the maximum of this function?
Maximum.
Again, maximum. But can you tell me what is the maximum?
1.
It's 1. Because before that, it was 0. When I add 1, it means that I am shifting all the previous values 1 unit upward. So when the maximum before was 0, now it is shifted upward. So is it understandable for everyone? So now let me ask you this question. So minus x minus 1 to the power of 2 plus 3. So you see this minus sign is actually very important. Yes? So what is this one? What is the maximum of this function? Yes?
3.
It's 3. And when it is achieved,
1x.
it's 1. So you see that this negative sign that appears here is actually very crucial. That's the intuitive way of understanding. So if I have a function of this form, okay, so this sign that you see here is somehow directly related to this number. If that number is negative, you will see, we will face some situation like that. So the parabola doesn't have a minimum, it has a maximum. And if A is positive, then you will see that because of the intuitive ideas here, it has a minimum. Okay? Okay, so now we understand that having a complete square is actually very handy in this case. Because if I have the complete square, if it is just a complete square, it's so simple. If it's a complete square plus any number or minus any number, I still can answer the question. So it motivates me, let us make a complete square out of it. And then it becomes algebra. So by this way of thinking, you find your strategy to how to tackle the problem. The problem is to make a complete square out of it. Now I think if you remember the quadratic rules and I don't know, squaring rules, things like that should be very easy. So let me remind you if you haven't, if you don't remember them. So what was the formula? Do you remember? This was a squaring pattern. If I have a binomial means a polynomial with just two terms. If I want to square it, what was the rule? Yes, Gustav?
A plus AB. No.
No.
What was it?
Yes?
A squared plus 2ab plus, no. Wait.
Plus
no.
B squared.
Plus b squared.
Right.
Yes? A squared plus 2ab. By the way, I have to kill myself, you know, because it was surprisingly you didn't remember. You should remember that. Yes.
You should.
Yes. Yes.
Yes.
Yeah, I think. Yeah. I hope that I can retire. You know, I don't commit suicide before that. So you need to remember. I have to beg you, please start caring about your memories. Okay. So a plus b to the power of 2 is this one, and then of course we have some similar thing. What's the answer?
A squared
Minus 2ab. So that's extremely important to remember these things, guys. Okay, so here I want to make it a complete square. So of course, is this you know that here from here to here we call it expansion. We are expanding this. Do you remember what was more or less the name of going back? We studied this direction when we were talking about identities and things like that. And then when we want to go back in this direction, so you see,
It's factorizing.
factorization. Thank you very much. So that's the factorization, yes? When I go here and write it in this way, why it's called factorization? Because when you have a product, each one of those numbers appearing in the product is called a factor. Why this is called factorization? Because a plus b to the power of 2 is actually a product. It is a shorthand way of writing this product. Yes, do you agree?
Yes.
So this means that when I go from the right hand side to the left hand side, I am factorizing this expression. Why? Because this is a product of two expressions, so that's a factorized form of that. So remember these words. From here to here, it's just identity or expansion. From this direction, it's factorized. Of course, can I factorize this, do you think? Let me ask you this question. If I give you this is probably the simplest possible example. Can you factorize this?
Yes.
What's the answer?
Well,
X plus 1 squared, yes? This is factorized form, yes? Do you agree with that? If you want to test your idea, go the other direction. The first one is squared, 2 times the first one times the second one is squared. Yes, do you have questions?
Oh, sure, I know how to do this. Should I?
No, I will come back to you, okay? So, this is a factorized form. But, if I write this, can I still factorize it?
Yes.
yeah.
No.
No.
Why not? You can.
Well, if you move
Can't you just,
the 2.
Okay,
the
tell
other
me, if
side.
you know the factorization, just tell it to me.
X squared plus 2x plus 1 plus 1.
That is not factorization, that's correct.
You can factorize
No,
that.
what you said is not factorization. Let me just remind you about this. What you said is completely true.
You did it
This is what you said, yes? Okay. This is what you said is 100% true. This equality is true. But this is not a factorization of that. Factorization means writing it as a product. If I ask you, read this expression in English. Let me ask you, is this a sum or a product?
What's the
So
sum?
It's a sum between?
Yeah, between 1 and x plus 1.
Okay, when you say that this is a sum, it is not factorized. When you say this expression is a product, then it is factorized. Okay, and that's completely right. What I need is not factorization in this problem. What I need is exactly what you told me. Is that understandable? So now, this is not 3, this is not 2, this is 3. So how can I write it?
2 plus 1.
Yes, x plus 1 to the power of 2 plus 2. Is that understandable?
Yeah.
Okay. So now, can I answer, do you think this function has a minimum or a maximum? Minimum or maximum?
Minimum.
It has a minimum. What is the minimum?
2
When it is achieved?
when x is minus 1.
Minus 1. So we were able to answer that, yes? Is that understandable? So, we were able, then the question is that, is it always possible to extract a complete square from a parabola? The answer is yes. Yes, the answer is yes, and if you want to do it, you can do it algebraically. Okay, we will do it. But let me tell you something. Here, so I would say minimum of y is equal to 2. It is achieved when x is equal to -1. Now I am asking you, can you give me the coordinates of the turning point? Yes, Abdullah?
-1, 2.
-1 and 2. Yes? So the turning point has coordinates -1 and 2. Do you remember, for example, if this is the minimum, this will go here. So this turning point, this x coordinate, is exactly the point where the minimum is achieved. And this y value is exactly the minimum value. So if I ask you what are the coordinates, you will say the coordinates are x and y. X is the point, is the x where the minimum is achieved, y is the minimum of the y itself. So this is the extreme point, or the turning point. Is that understandable? So what we want to do, we want to follow this strategy. Of course, if we do, let me make another one with negative value. Let me see how do you answer that. So when the lesson ends, do you know?
No.
13:05.
Okay, we have still time. Okay, so here, let me make something with negative. It is a little bit, might be a little bit, let me make it minus x squared plus 2x plus 3. What is your intuition? Do you think this will have a max or a min?
Max.
It should have a max, yes, because we were intuitively clear, because this is negative. Okay, now, I told you a different trick last year, I don't know if you remember. How do you evaluate this problem now? So I want to find again the turning point, but this time you know that the turning point is not a minimum type, it's a maximum type. Yes?
Are you thinking of putting the negative sign on the other side?
Yes, do you remember that was the trick that I told you, yes?
Hmm?
Okay, do you have any other idea? I'm not saying that this is the only idea that I taught you last year, but this is a very good way,
I was
yes?
thinking of using the same strategy, but putting the negative sign in front of it, the x plus 1 squared.
Okay, then you need to, yes, that's completely okay. That's working if you write this and it's not okay with me. But you need to be careful about adjusting the signs and the numbers in a way that everything goes back to the same original form. If you trust your algebra like that, that's completely okay with me. But another way that I was thinking, I would multiply this by minus sign. Okay, this is my experience. So I multiply it by minus sign. It becomes minus y. This becomes x squared minus 2x minus 3. Okay? This is easier in practice because minus signs are actually nasty things, you know. If you lose them, you will actually lose the points and things like that. So my preference for you, of course, you see I am not forcing you to follow my rules. I'm just trying to tell you, might be, I don't know, this is the simplest way to do. But if you do it correctly in the exam, I would be more happy actually to see your own way. So I will do this. And now momentarily, I will repeat minus y, but I will use the same trick here. So what can I do? Can you tell me, how can I extract a complete square out of it? Just tell me, someone else. Yeah, try to actually be engaged, otherwise you get bored immediately. Anyone? Back of the classroom. No one? I'm just asking you to do the same trick here. I want you to have a complete square for me. And some extra terms might be. Yes, please. So just may you speak louder. So what should I write?
X squared minus 2x. And then can you move it? Then just minus 1 plus 2.
Like this? Like this?
No.
Because minus 1 plus 2, minus 1 minus? Minus 1 minus 2 is correct. So what you have written is correct, but is it useful? Minus 1, minus 2, I agree with you. It is minus 3. X squared is x squared minus. So everything you have written is completely true. But is it useful?
Yeah.
No. Be careful about one single thing. Is this a complete square now?
Ah, no.
Why not?
Be positive.
Because this one is negative.
Yeah.
Right.
So you have to have that one positive.
Yeah.
Okay, but how can I fix that? Okay, I like positive, I put positive.
Yeah.
But I need to do something to compensate for that. What should I do?
-4.
Negative 4. Yes? So this is something you really don't need a teacher. You need to know, understand the logic. You can just discover it whenever you need it. Okay? So I just wrote it in this way. And let me just go one step. So what happens here?
X minus 1
X minus 1 squared minus 4.
minus 4, yeah.
Okay. Now forget about, momentarily don't see this. Do you think this expression has a minimum or a maximum?
Max.
Minimum.
Minimum.
Yeah.
Yes? I'm just asking about this expression.
Oh, you didn't.
This has a minimum.
Yeah.
Okay? So what is the minimum? So if I ask you what is the minimum of this expression?
-4.
The minimum is minus 4. What does it mean? It means that this expression, which is minus y, is greater than or equal to minus 4. Yes? Because you just told me that the minimum of this expression is minus 4. You are right. But this expression has another name, which is minus y. And you said minus 4 is its minimum. So it means minus y should be greater than or equal to minus 4. Is that understandable? But if minus y is greater than or equal to minus 4, I don't want to talk about minus y. I want to talk about y itself.
Multiply.
You have to multiply by a negative sign to get rid of this negative sign that you brought it in.
Yeah.
Okay? And if you multiply, it becomes y. If you multiply this by a minus sign, it becomes 4, and what happens?
But it's
You
less
switch
than
the-
Yes, we have to switch the sign.
Yeah.
Yes, because we are multiplying by a negative sign. And now interpret
No, whoa,
this.
whoa, whoa.
You didn't
Baba,
switch it.
Hold up now.
Oh, sorry. I have to switch.
Baba.
Like, don't kill me, okay? Just switching. Okay. So y is less than or equal to 4. What is the meaning? Y is smaller or at most equal to 4. So what does it mean? It means y maximum is
4.
4.
Yeah, isn't that the maximum of the parabola?
Yes.
4.
Yes. We just wanted to find the maximum.
But you said it didn't have a maximum. It had a minimum.
No. If I did it wrong. No, but as soon as this is a negative, I realize that there is a maximum. Might be I have made a mistake when I was talking about it. Yes. So you find your maximum. Okay, now can you tell me what is the turning point? What are the coordinates of the turning point?
1
1,
and 4.
4.
Yeah.
What type of point is this turning point? Is a local maximum.
Yeah.
Or in this case, we don't need even to bother about saying local. That's just the maximum. Yes? The maximum, because there is only one unit of this.
Yes.
So the only thing that can happen is that you have this algebraically harder. By more nasty numbers like fractions or having some numbers here, make it a little bit harder. But that the algebra is the same. I myself prefer to make it always equal to 1 by dividing by this number here. Here actually I divided by minus 1. If I had another number, so let me just do this quickly. So let us see what happens here. So if I have this y equals to, for example, minus 2x squared plus, yes, let me just, make it a little bit harder, okay? So these are a little bit bad numbers. You have to start working with fractions, but the ideas are the same. So first of all, what is your guess for this? Is there a maximum or a minimum?
There's a maximum.
There is a maximum, exactly, because this one is a negative one. I don't know how do you want to do it. You can follow your own way, but if you want to follow my advice, is to get rid of this coefficient. So how can I get rid of this coefficient? I divide by minus 2. When I divide by minus 2, it becomes minus y divided by 2. This becomes x squared minus 3 over 2x, and then plus 1 over 2. So you have to be just careful, that's it. Okay? And now, of course, it is a little bit harder to guess how to extract the complete square, but that is just the complete square. So can you extract the complete square out of it?
You can.
Yes, but how? Or you just tell me how to do it, I do it.
-3 divided by 2 divided by 2.
2 and squared. Yes? So that's the idea. Actually you did it here. How did you come up with 1 here? Because you wanted a number so that 2 times the first one times the second one becomes -2. Yes, this is the second one squared which is written here. So you go to a scratch paper here. You divide 3 over 2 by 2 immediately. What's the answer?
3 over 4.
3 over 4.
Yes.
And then square it. 9 over
16.
16.
Yeah.
So, what you do, you write x squared minus 3 over 2x plus 9 over 16. But I cannot just add 9 over 16 there. I have to compensate for that. But I have also an extra 1/2 here. So you see, the concept is not harder here. Algebra is harder. That's it. Not, I am saying harder. Yes, it is harder than the previous one. But harder doesn't necessarily means hard. Yes? It's harder, but not hard. Okay, now can you tell me how should I go on? These 3 makes a complete square for me. Can you tell me? Can you read it for me? X minus
9 over 16.
No.
Isn't it?
No. Minus what to power 2?
3 over 2?
3 over 4.
3 over 4.
Because I need a number so that after being squared becomes this.
Right.
Okay? So that's the number. And if you don't believe that this is the right number, just check the idea. 2 times the first one times the second one. 2 and 3 times over 4 exactly becomes 3 over 2. So everything is correct. Mm-hmm. And now, what is left for me? This is left for me. But no one writes this. We go to scratch paper again. We calculate that number. Minus 9 over 16. Instead of 1 over 2, I write 8 over 16. Agree with me?
Mm-hmm.
And then if I add them, it becomes minus 1 over 16. So I write minus 1 over 16. Okay? Yeah, we are finishing now. So actually it was a good warm-up, I think, because we remember actually a lot of things. But you don't need to go through this trouble later. We just learn derivatives. If you learn derivatives, calculating is very, very simple. But just tell me, what should I do? Is there any minimum or maximum? What is the maximum? What is the minimum of this function?
Minimum?
Yes, what's the minimum of this?
3 over 4.
It's minus 1 over 16, the minimum.
Okay.
Yes? So it means that minus y over 2 is greater than or equal to minus 1 over 16. I multiply by negative 2, it switches the side and it becomes 1 over 8. So this means that maximum of y is actually 1 over 8. Yes?
Yeah.
That's the maximum of y, and if I want you to find the turning point for me, the turning point is 3 over 4 and 1 over 8. Okay, so this was the last session that I was repeating. I don't know, in the digital book you don't have page number, but there is something on top of that you will see, a repetition here. So I end up the lesson until this. Next time I will start the new lesson, which is actually very important. Okay. No questions? Thank you very much.